Let's move on to the second part. What is a solution? What is a suspension? Now we learned about a homogeneous mixture. Now let's shift our focus to heterogeneous mixture and let's learn about what is a suspension. A suspension is a heterogeneous mixture in which the solute particles do not dissolve but remain suspended throughout the bulk of the medium. Particles of a suspension are visible to the naked eye. So, like we had taken a homogeneous mixture to be a solution, similarly, we are equating a heterogeneous mixture to be a suspension. What happens in a heterogeneous mixture? We know that there is no uniformity, we know that there is no stability. So, in the absence of these two, the solute particles, they do not dissolve into the solvent, but rather they remain suspended. I told you that they remain suspended in the sense that they are basically sort of trapped in between the solvent molecules. All right. So, for example, in this picture here, you can see that oil is suspended in water molecules. All right. So, you do not observe a very uniform mixture of oil and water. What you rather see is that oil molecules, they are trapped, they are suspended, they are hanging in between the water molecules. All right. And that they remain suspended throughout the bulk of the medium. It's not that they're only suspended through here and not towards the upper part and not towards the bottom part. Even though the upper layer has more oil molecules than what we have in the bottom, but still the upper part, oil molecules at the upper part, they are still suspended there, right? And the other most important quality of a suspension is that particles of a suspension are always visible to the naked eye, the same difference that we had previously established between a homogeneous mixture and a heterogeneous mixture. Now, what are the properties of suspension? Like we had studied the properties of solution, let's study about the properties of suspension. Suspension is a heterogeneous mixture. This we have established, all right? So, we know that particles of a suspension can be seen by the naked eye, and we also know that since the particles can be seen by the naked eye, so they are very distinct. Suppose this is a beaker of oil and it has water as a solvent, and also it has oil molecules as a solute. So the oil molecules, they may be either suspended at the top or at the bottom or in the middle somewhere, all right, but they are very distinct molecules that are visible to our naked eye. So if we, if we take a torch and if we make its light pass through the beaker, all right, what we will notice is that light is being scattered all around. And why? Because in like previously we had the sugar solution or the salt solution that obtained a homogeneous mixture, so there were no particles to scatter the light, right? You need, the light should bounce off a surface, right? So if this is a surface and light is striking here, it should scatter around, it should bounce off a surface. So in the absence of the solute particles, light was just passing through. But since we have particles suspended in the solvent here, so we can see that when we scatter a beam of light passing through it, it's make its parts visible. The particles suspended in the solvent, they scatter the light. So solute particles, they settle down when a suspension is left undisturbed. That is, a suspension is unstable. So after a while, you may observe that the oil molecules have settled. And since oil is light intensity than water, so oil will form a sort of flimsy layer at the top of the water molecule. So basically, they have settled somewhere, right? So they are unstable, and this kind of mixture, it cannot be separated. The components of the mixture cannot be separated by the process of filtration. So like we had in the homogeneous mixture, that the components cannot be separated from each other through physical methods such as filtration. In contrary to that, in a suspension, since a suspension is a heterogeneous mixture, the particles, they can be separated from the mixture by the process of filtration. So even it may not be very similar for the oil or water thing, but mostly in suspension, what you will observe is that by the process of physical methods such as filtration, the components, they can be separated. Why? Because obviously the solute is visible to the naked eye, so they are bigger chunks of particles, right? So they can be easily separated by the process of by some physical process. When the particles settle down, the suspension breaks and does not scatter light anymore. Yes, so when the particles settle down, The suspension breaks because now the particles are not suspended, they are basically settled, be it at the upper layer or the bottom layer, and because they are now settled at one particular place, then the light, they cannot reflect the light, they cannot scatter the light. What is a colloidal solution? The particles of a colloid are uniformly spread throughout the solution. Due to the relatively small size of particles as compared to that of a suspension, the mixture appears to be homogeneous, but actually a colloidal solution is a heterogeneous mixture. Now we have established that suspension is a heterogeneous mixture and solution is a homogeneous mixture. But there is another category of solution, that is a colloidal solution. And what is a colloidal solution? Colloidal solution is basically a heterogeneous mixture, but it appears to be homogeneous. So the particles of the colloidal solution, they are smaller in size, and because they are smaller in size, so they appear to be homogeneous, but in actuality the solution is a heterogeneous mixture. For example, milk and fog. So we had seen, if you remember, one of the very first experiments in this chapter was that we had added few drops of milk to water and we had stirred it. So the milk solution, it may appear to be homogeneous, but it is not. It is actually a heterogeneous mixture, and it is actually a colloidal solution. Fog. Similarly, when we have some particles of smoke and dust and water and everything, when they get mixed into the air molecules, the resulted solution, it appears to be homogeneous, but it is actually heterogeneous in nature, and it is a colloidal solution. Tyndall effect. Scattering of a beam of light by particles is called the Tyndall effect, after the name of the scientist who discovered this effect. Tyndall effect can also be observed when a fine beam of light enters a room through a small hole. This happens due to the scattering of light by the particles of dust and smoke in the air. Now, we have already established in the previous experiments that when light passes through a solution, and when that solution has very obvious solute particles in it, in other words, when the solution is a heterogeneous mixture, so those particles of the solute, they scatter light, alright, they scatter light in various directions. So this property, the scattering of a beam of light by particles, is called the Tyndall effect, and this is named after the scientist who discovered it. A Tyndall effect can also be observed. So you may have observed that, for example, if you switch off the lights of your room and during the daytime, and when you open a window, so you may see that, you can see a very visible, like this shape, you can see a very visible path of light in the air, and you can also see particles, tiny air particles flowing into that light, they're suspended into that light, right? So basically these are suspension, all right, the particles, the different constituents of air, it can be dust, it can be smoke, it can be even water molecules. So these particles, they scatter the light, and since they are scattering the light, they are making themselves and the other particles in the air visible, all right? So this is a very clear demonstration of Tyndall effect. Tyndall effect is also observed in forests. How? So Tyndall effect can be observed when sunlight passes through the canopy of a dense forest. In the forest, mist contains tiny droplets of water which act as particles of colloid dispersed in air. So what happens in a forest is that, so they are very tall and very huge trees, shrubs and all that. So when two and more trees, they form a canopy sort of structure when viewed from above, right, when an aerial view is taken. So you can see that light is passing in between those tall trees, all right. So if there are two or more, there are huge trees, right? So light is passing through those trees, and the water molecules, the mist, you may say, that are suspended in air, that those water molecules suspended in the air, they are mist. So they scatter the light, and because of the scattering of the light, as you can observe in this diagram, this sort of sight is made visible to us. So this is because of Tyndall effect. Properties of a colloid. Now we have seen what a suspension is, we have seen how a colloidal mixture is basically a heterogeneous mixture, but it appears to be homogeneous, but is actually a heterogeneous mixture. Now we will observe the properties of these colloid. Colloid is a heterogeneous mixture, this we have established. The size of particles of a colloid is too small to be individually seen by naked eyes. That is why we sometimes may mistake colloid to be a homogeneous mixture. Colloids, but the particles of colloid, they are small to be seen to the naked eye, but they are big enough to to scatter a beam of light passing through it and makes its path visible. The air coming out of the window in a dark room, or the Tyndall effect observed in the forest, all these are properties of colloid. And they do not settle down when left undisturbed. That is, colloid is quite stable. Another property as to why a colloid could be, could be perceived as a homogeneous mixture, but whereas it is heterogeneous one. So they cannot be separated from the process of filtration, but a special technique of separation known can be used to separate the colloidal particles. So basically, colloid mixture, they cannot be separated by physical process such as filtration, that similarly like we had in homogeneous mixture. So to negate that, we have a special technique, and that we'll be using to separate the components from the colloidal particles. What do the dispersed phase and dispersion medium convey? The components of a colloidal solution are the dispersed phase and the dispersion medium. Likewise, you can understand this as like a solution. Like a solution had two components, right? Solute, the amount that was added to be dissolved, and solvent was the substance into which the solute was added to be dissolved. Similarly, in colloidal solution, the dispersed phase is you can equate it to the solute, and the dispersion medium you can equate it to the solvent, meaning that the solute-like component of the dispersed particles in a colloid, they form the dispersed phase, alright, and the component in which the dispersed phase is suspended. So like solute was dissolved into the solvent, equivalently the components, the dispersed components that are scattered there, that are around the in a colloidal mixture, so they are around the dispersion medium. So dispersion medium is what a solvent is there in a solution. So component in which the dispersed phase is suspended is known as the dispersing or the dispersion medium. What do the dispersed phase and the dispersion medium convey? Like we have in this example, we can see oil. When you dissolve oil in water, immediately it takes time to settle down, but immediately you have a colloidal solution. Oil, since it is being dissolved in water, oil is the dispersed phase and water is the dispersion medium. Classification of colloids. You can classify colloids by the basis of the dispersion phase and on the basis of the dispersion medium. So there can be different forms of dispersion phases dissolved into different sorts of dispersion medium. Colloids are classified according to the state. All right. So the dispersed phase, they can occur in different states, right? They can occur in either solid, liquid, or gas. And similarly, the dispersion medium, they can also occur in these three states: solid, liquid, and gas. So we classify colloids on the basis of these difference in the states. Aerosol. Aerosol is a colloid. In aerosol, the dispersed phase is liquid, like the solute equivalent is the liquid, or it can also be a solid, but mostly it's a liquid, and the dispersing phase is gas. So fog, right? Fog, we have particles, solid particles suspended in gas. Clouds, we have water droplets suspended in gas, as in the air. Smoke, again, that's we have solid particles suspended in gas. Automobile exhaust, we have solid particles suspended in gas. It can also be mist. Mist also has water droplets suspended in gas, right? So these are examples of aerosol. Foam. What is foam? In foam is a sort of colloid in which the dispersed phase is gas and the dispersing medium is a liquid or a solid. Examples are shaving cream. Shaving cream, if you see how a shaving cream comes out of the bottle, right? So it is very foamy, right? It has tiny droplets of air. So these air molecules, they are basically suspended in that liquid cum solid texture of the dispersing medium. Similarly, sponge, air molecules, air sacs, they are trapped in between the solid structure of the sponge, and same goes for the pumice stone. Examples of emulsion. Now, emulsion is a liquid-liquid phase. So, we have observed like liquid-solid and gas, and we have observed in the previous state that was foam where we had gas in the liquid-solid state. Now, we will be observing liquid as the dispersed phase in the liquid dispersant medium. This is known as emulsion, and examples can be milk and the face cream, the cream that you apply on your face or the lotion that you apply on your body. These are examples of emulsions. Sol. Now, what is sol or sol, however you may pronounce it? Sol is the dispersed phase, and the sol is a solid, and the dispersant medium is the liquid. So, mud, a very classic example of sol is the mud. We have solid particles, solid soil particles in water, so muddy water, right? As you can see in this diagram here, this cute diagram. So, that is example of sol. Milk of magnesia is also an example of sol. You have solid particles suspended in the liquid dispersing medium. Gel. What are gels? Gels are colloids in which the dispersed phase is the liquid and the dispersing medium is the solid. So, like butter, right? So, butter is very creamy unless it is frozen, right? So, butter at room temperature, it's very creamy. It is because there are some liquid particles that are, suspended in the solid chunk, in the solid dispersion medium or the dispersing medium of the substance. Same goes for jelly. Jelly is very gooey. Okay, so you cannot call jelly a whole solid. It has some liquid particles that are suspended there, and that what gives jelly that bouncy structure that it has. And same goes for cheese. Solid sol. Now, we learned about sol, but there is a solid sol. So, solid sol, as it is very convenient from the name, that is, the dispersed phase is solid and the dispersing medium is also solid. This example can be seen in colored gemstone and in the milky glass. In the big glass tumblers that we have in certain restaurants, these are examples of solid salt. Question 1. The first question is, differentiate between homogeneous and heterogeneous mixtures with examples. So we know that homogeneous mixtures are also known as solution, alright, and heterogeneous mixtures, they are also known as suspension. And we know that homogeneous mixture, they have a very uniformity to its whole structure. The structure is very stable. The properties, the components, they cannot be, separated from each other with the help of physical processes such as filtration. Whereas in heterogeneous mixtures, there is no uniformity, there is no stability, and the physical processes such as filtration, they can be used to separate some components, in some of the heterogeneous mixtures. How are sol, solution and suspension different from each other? So, sol is an example of colloidal solution, alright, and solution, as we have seen in the previous question, it is an example of, solution is basically a homogeneous mixture and suspension is basically a heterogeneous mixture. So, sol may be a colloidal and it may be a heterogeneous mixture, but the difference is that it appears to be homogeneous, it has some qualities of homogeneous mixture, but all in all, it is a heterogeneous mixture. Question 3. To make a saturated solution, 36 grams of sodium chloride is dissolved in 100 grams of water at 293 K. That means we are having some amount of solute that is being dissolved in some amount of solvent at a given temperature, and we need to find its concentration at this temperature. So it's a very easy question, right? We just need to find its concentration. So first, we will look at the mass of the solute. So mass of the solute here is 36 grams of sodium chloride. Then we will have a look at the mass of the solvent. So mass of the solvent, here is the water, and mass of the water is 100 gram. Now, to identify the concentration, to calculate the concentration, we need to equate the mass of the solute. We need to relate the mass of the solute in relation to the mass of the solution. And what is the solution? Solution is the mixture of solute and solvent. So what will be the mass of the solution? Mass of the solution would be the mass of the solute plus mass of the solvent. So that means 36 plus 100, that is 136 gram. Now it's easy, right? We have mass of the solute, we have mass of the solution, and we have one particular given temperature. The temperature is neither increasing nor decreasing. Now we just need to find its concentration at this temperature. So therefore, concentration could be calculated as mass of the solute that we have divided by mass of the solution into 100, right? So mass of the solute, we had 36 gram, that we will divide it by 136 gram and we will multiply it by 100. Why? Because we need to, concentration is always calculated in percentages, right? So we need to have a certain percentage at which the concentration of the solution is to be observed. So when you calculate this, you will get 26.47 percentage. That is the percentage that 36 gram of sodium chloride, when it is dissolved in 100 gram of water at 293 Kelvin, this is the concentration that you will get. Now we will have a look at separating the components of a mixture. Why do we need separation? We need separation because different methods of we need separation because the separation makes it possible, and it makes us human beings convenient to use those individual components of a mixture. So suppose we have a solution of milk and water, but we need milk, right? And we may need water, okay? So in order to obtain, and we only have that source, say we only have that source and we need to obtain milk or we need to obtain water. So we need to come to discover a method by which we can separate those two components and we can get them so that we can use them, right? So we need separation. Separation makes it possible to study and use the individual components of a mixture, and different methods of separation are used to get individual components from a mixture. Heterogeneous mixtures can be separated into their respective constituents by simple physical methods, right? Like hand picking, sieving, filtration that we use in our day-to-day life. So we know, we have established this fact earlier as well, that physical processes such as sieving, filtration, also hand picking, they can be used to separate constituent particles in a heterogeneous mixture. And there are sometimes special techniques that we need to use for the separation of components of a mixture. Now let's have a look. How can we obtain colored component from ink? So for this, we are performing an experiment. We are taking half a beaker and we are filling it with water. Then we are putting a watch glass. This is a watch glass, as you may see in the diagram, this tumbler sort of, utensil. So we are taking a watch glass and we are adding few drops of ink to the watch glass. Now start heating the beaker. We do not want to heat the ink directly. You will see that evaporation is taking place from the watch glass, and continue heating as evaporation goes on, and then stop heating when you do not see any further change on the watch glass. So what is happening here is we are not directly heating this ink. We are first of all taking a beaker, we are filling it with water, we are heating that beaker of water, and then we are allowing that ink substance to be heated indirectly from the steam that must be forming in that beaker and that must be coming into contact with this watch glass, with the bottom surface of this watch glass. So we are indirectly heating the ink, and because we are indirectly heating, we are causing an evaporation to occur. Alright, so when this evaporation occurs, we observe that water is evaporated from the ink and we are left with only the colored component or the residue on the watch glass. So ink is basically a mixture where you have water, alright, and you have the dye. So this may be called a suspension, right? And you have water as the dispersion medium and dye as the dispersed phase, and ink is a mixture of dye and water. Thus we can separate the volatile component, that is the solvent, from its non-volatile component. Volatile means the one which is able to evaporate, very easily. So solvent is able to evaporate very easily from its non-volatile solute, that is the dye. Alright. So when we indirectly heat it, the solvent evaporates and we get the residue, that is a dye, and that is how we obtain the colored component from ink. How can we separate cream from milk? There is a very special process for it, and that is known as centrifugation. Now, you must have heard of this term. Centrifugation, what happens in that, we are basically involving, it has a very, machine, it has a very circular machine sort of structure in which there is a fixed axis, all right, and on the, the radius of it, you have some test tubes or some it's a test tube sort of structure that is fixated, and then a force is made to revolve this structure, this circle sort of structure in a circular motion. So what is happening? The force is radiating outwards, right? So in centrifugation, when we have to separate cream from milk, so we take some full cream milk in a test tube and we centrifuge it by using a centrifuging machine for 2 minutes. This is how a centrifuging machine basically works, okay? And if a centrifuging machine is not available, then you may do this at home by using a milk churner. So this was basically how cream was separated from milk. It is still being separated. If you go to some villages, or it can also be performed at home as well. Sometimes your mother, or your sister, or your aunt, and your father, anyone in your home, they may they may churn, they may cause the milk to rotate in a very circular sort of fashion. And when that happens, you are basically allowing the cream to be separated from the milk. All right. So in centrifugation, what happens is that force is applied outside, and that is how the machine works, and that is how the process is, and that is how you get the cream from the milk. Observation will be that 2 layers are separated from milk, and we obtain creamy layer on top of the test tube. And the principles for centrifugation is that the denser particles are forced to the bottom, and the lighter particles stay at the top when spun rapidly. So milk being the heavier component, it stays at the bottom, whereas the cream being the light fluffy component, it settles at the upper portion of the mixture. Applications of centrifugation. Now this is a very basic process, but so in this diagram, you see this right picture. This is the centrifuging machine, all right. So this is the fixed axis, all right, and these are small test tube sort of structure that are used, and this is basically rotated, and that is how the different components are separated. So centrifugation is an application that is used in diagnostic laboratories for blood and urine tests. It is used in dairies as well as home, like from that example in the previous slide, butter to separate butter from cream, to separate cream from milk, and it is also used in washing machines to squeeze out water from wet clothes. So your washing machine also uses this process of centrifugation when you have that drying option, right? So this process of centrifugation is used. How can we separate a mixture of 2 immiscible liquids? Immiscible liquids are liquids which cannot be mixed together, okay? Cannot be mixed together to form a very homogeneous sort of solution. So let us try to separate olive oil. We know that oil does not dissolve in water. It is sort of suspended in water. It forms a heterogeneous mixture. So let us try to separate olive oil from water using a separating funnel. So we have taken a separating funnel, we have added olive oil over here, and we have added water over here, and we have let it stand undisturbed for some time, so that separate layers of oil and water are formed. This happens whenever you take an oil and water mixture. So we open the stopcock. Here is the stopcock, this thing over here, and we open the stopcock very carefully, okay, so that the lower layer of water is collected in this bottom beaker or this bottom tumbler. So we are basically opening the stopcock till the level of till all the water is being separated out of the separatory funnel, and as soon as we reach the water surface, we close it. All right, so close the stopcock of the separating funnel as the oil reaches the stopcock. Observation: we get water and oil in separate beakers, and the principles of separating funnel is that immiscible liquids which cannot be mixed together, separate out in layers depending on their densities. Do you know where this technique is used? to separate the mixture of oil and water that we have just established in the previous experiment. But there is a very important industrial application. This is also used in extraction of iron from its ore. All right. Now, iron, which you use in your industry, in your home, and various places. So iron, it does not exist like that basic pure substance in nature. All right. It exists as an iron ore. What this iron ore has, obviously it has that pure iron, all right, but in addition to that it has a lot of impure substances, and those, let us name that impure substance as slag. All right, so that impure substance is basically light and the iron is heavy. So by the process of using the separating funnel thing, the lighter slag is removed from the top by this method to leave the molten iron at the bottom and the surface. So in a very heavy scale, in a very large scale, this application is used in industries to separate iron, molten iron, from its lighter, dirtier slag, and that molten iron from its ore can, it will be processed to further applications to be obtained in its pure form. How can we separate a mixture of salt and camphor? Salt and camphor, both of these are solid structures, solid substances. Let us determine. So camphor changes directly from solid to gaseous state. We know this. We learned about this in our previous lesson. A transition from a solid state to a gaseous state without reaching the liquid state. What is this known as? This process is known as sublimation. So camphor, like ammonium chloride, is another substance. Camphor is your kapoor, which must be used in your home during puja, or just to light up the room, right? So camphor changes directly from solid to gaseous state on heating. So to separate such mixtures that contain a sublimable volatile component from a non-sublimable impurity, the sublimation process is used. Some examples of solid which sublime are ammonium chloride, naphthalene, that is your naphthalene balls that are used, mothballs, right? That are used in while you keep your big chunks of, especially your winter clothes, to protect them from moth, and anthracene. In this experiment, we have taken a china dish, we have taken an inverted funnel, and we have added in that china dish, the bottom is the solid salt and the camphor mixture, all right, and we are providing heat to this setup through a burner. So what is happening is, when heat is provided, this camphor it starts vaporizing. Okay, so evaporating, vaporizing, whatever term you may use it, but the technical term would be that it starts sublimating. Why? Because it's changing it from its solid state to a gaseous state, and when it reaches the not so heated part of the inverted funnel, the long stem, or maybe this area, right, this area, so there is the deposition of the solidified camphor, because that part is not as warm as just the bottom part of the inverted funnel, and that is how you may obtain camphor from its salt mixture. Is the dye in black ink a single color? Take a thin strip of filter paper, or this filter paper you may also name it as the chromatography paper. Why chromatography paper? Because we are using this paper to obtain different colors that will be obviously demonstrated in this experiment. So let's have a look. Draw a line on it using a pencil approximately 3 cm above the lower edge. Put a small drop of ink at the center of the line, and let it dry. Then lower the filter into the jar, glass, beaker, test tube containing water, so that a drop of ink on the paper is just above the water level, and then leave it undisturbed. Watch carefully as the water rises up on the filter paper. So what we are doing here is, we are taking a filter paper or a chromatography paper, we are drawing a sort of pencil sort of line in between, okay, and just in between at the bottom place we have placed one drop of ink. We have allowed that drop of ink to dry first, then we have taken, say, water into a jar, glass, beaker, test tube, whatever manner you may seem fit, and then we have made that filter paper to come into contact with just the surface of the water, that is you see here in the small animation. Okay, what happens next? As water rises on the filter paper, so when we are adding extra water, we are, adding the water, we are causing the water to rise on that level. We observe that the single dot of ink, it spreads into multiple spots of different color, and the dye in blank ink that can be concluded is a combination of more than one color. So when water is allowed to pass through it, we observe that, as you can see in the small animation, you see it is splattering into different colors, right? Blue, red, yellow, okay, other substances. So from this experiment, we can conclude that the black ink, that dye, is not a single color, but it is a combination of more than one color. What can be the reason for the rise of the colored spot on the paper strip? The ink that we use as water as the solvent and the dye is soluble in it. Okay, okay, this is very easy. The ink that we use has water, that has already been established earlier, and the dye is soluble in it. All right, dye is the solute, we know it. As the water rises on the filter paper, it takes along with the dye particles. Usually, a dye is a mixture of two or more colors. The colored component that is more soluble in water rises faster, and in this way, the colors get separated. So, what is happening here is, since one part, the solvent part, it also gets washed away with the water, and the solute particles, there must be different components, right? They are different components, and the solubility of those different components must be different. So what is happening is that when that colored component is, when water is made to pass through it, so that colored component that is more soluble in water, obviously that will rise faster, because that will tend to move along with the water. Why? Because that is more soluble in water. So the particle that is more soluble in water will tend to move along the line of the water, and the particle, the colored component that is less soluble in water, will tend to lag, right? It will be near the bottom of the paper. All right, that is how we demonstrate, and that is why the reason, that there is a reason for the rise of the colored spot on the paper strip. Chromatography. So the separation of a mixture by passing it in a solution through a medium in which the components move at different rates is known as chromatography. Basically, the previous two, the previous experiment and the previous observation that we obtained, that we saw from the experiment. Chroma in Greek means color. All right. So chroma in Greek means color, and so chromatography is basically how is the separation of mixture by passing it in a solution through a medium in which the components move at different rates. This technique was first used for separation of colors that we simply saw in that ink and dye experiment. So this name was given. Chromatography is a technique used for separation of those solutes that dissolve in the same solvent. So those dye particles, all of them, all of the dye particles, red, blue, yellow, that had its, that gave its black color, but the black color was basically a mixture of all those components, right? So all these solutes, they were dissolved in one solvent, they were dissolved in water, right? So by the method of chromatography, by the technique of chromatography, we can separate those solutes that dissolve in the same solvent. Okay, applications of chromatography: to separate colors in a dye, of course; to pigments from natural colors, yes; drugs from blood. Okay, so the kind of solutes that are dissolved in the same solvent. Activity: how can we separate a mixture of two miscible liquids? Now we know that we can separate two immiscible liquids by using that separating funnel technique. Now how can we separate a mixture of two miscible liquids? Two miscible liquids means two liquids which can intermix with each other. Let's try to separate acetone and water from the mixture. Let the mixture, take the mixture in a distillation flask, fill it with a thermometer, heat the mixture slowly, keeping a close watch at the thermometer. The acetone vaporizes, condenses in the condenser, and can be collected from the condenser outlet. Water is left behind in the distillation flask. So what we are observing here is that we have taken this flask, is known as the distillation flask. We have taken the distillation flask, we have added a thermometer, and then we have connected this distillation flask to a water outlet clamped to a water condenser, and the mouth of this water condenser is opening up into another beaker. What is happening here is, when we are adding heat, the acetone, alright, the acetone has a lower boiling point than water. So acetone boils first, alright, it is boiling, and the vapors, they, since this is blocked here by the thermometer, so the vapor, they will naturally go into this direction, to the water clamp outlet. This is a water condenser. So in the condenser, through the process of condensation, the vapors of the acetone, they're converting back into the liquid stage, and that, since the mouth of the condenser is opening into another beaker, so we are getting over here acetone. All right, we have this cold water in the condenser. You may see this thin strip of water, cold water, that provides heat for the gaseous molecule to absorb. Then condensation takes place, and we are getting acetone. That is how we separate acetone from the mixture of water. We observe that as temperature rises, acetone starts to vaporize, and at the boiling point of it, the whole acetone separates out from water. We can conclude that from the distillation method, this method is distillation. From the distillation method, components of a mixture containing two miscible liquids, two liquids which can mix with each other to form a homogeneous mixture, right? They miscible liquids that boil without decomposition and have sufficient difference in their boiling points can be separated. So a basic of about 25 degree is taken, right? So if two liquids have more, the boiling point between those two liquids, they differ more than, they have a difference of more than 25 degrees Celsius or 25 Kelvin, then they are said to be, they can said to be separated from each other through the process of distillation. What do you mean by fractional distillation? Now, what about two liquids that cannot be separated from each other by the use of distillation? So, what about two liquids who do not have vast differences in their boiling points? For that, we come to the method of fractional distillation. To separate a mixture of two or more miscible liquids for which the difference in boiling points is less than 25 Kelvin, fractional distillation process is used. For example, for the separation of different gases from air, different fractions from petroleum products, etc. The apparatus is similar to that for simple distillation, except that a fractionating column is fitted between the distillation flask and the condenser. So this is the whole apparatus. The only difference, if you may notice, is this fractionating column. So this may appear very small, okay, but what is happening in the fractionating column is that there are small sort of bar, very minute bar-like structures, and this is again opening up to the water condenser area. Okay, so what happens is when with one of the miscible liquid, when they do not have vast difference in their boiling point, when it evaporates, it goes through this fractional distillation where there must be difference in between the temperature, right? Since this is closer to the whole setup, this will have more temperature than this, okay? And when you, this has only one water condenser outlet, but when you use the setup in a large scale in industries, for example, when you have to separate huge mixtures, mixtures who have more than two solutes in the solvent, right? When you have to separate that, you may use more than one outlet for this fractionating column, and so that, you know, if you're using more than one outlet, what is happening is that, say solute A is has to evaporate at a certain temperature, solute B has to evaporate at a certain temperature, and C has to evaporate at a certain temperature. So both, all of these, they are exiting this distillation flask from their own, whatever their temperature, respective temperatures are, and they are going through the condenser and they are collecting respectively in different containers. So this is just for maybe this setup may be used for two components, as in key two solutes in one solvent, or maybe two components mixed into each other. But when you have two or more components that are mixed into each other, then you may use more outlets out of this fractionating column. How do we obtain different gases from air? We obtain different gases of air from fractional distillation. Air is a homogeneous mixture, we know that, but this can be separated into its components by fractional distillation. If we want oxygen gas from air, we have to separate out all the other gases present in the air, right? So the air is first, we have to first obtain air in the liquid state. So we compress the air by increasing the pressure, and then we cool it down by decreasing the temperature, so that the random molecules of air, the huge spaces in between the particles, they can be curved, right? So these particles, they can be lessened, right? So we decrease the temperature to do that, to get the liquefied air. And once we have got the liquefied air, then we allow it to warm up slowly in a fractional distillation column, where gases get separated at different heights depending upon their boiling points. A brainstorming question. Sorry. Arrange the gases present in air in increasing order of their boiling points. Which gas forms the liquid first as the air is cooled? So liquid nitrogen, okay, liquid nitrogen is the first gas that will come out, all right, because it has the lowest boiling point. So first we will have nitrogen, then we will have argon, then we will have oxygen, then we will have carbon dioxide, and then we will have water. So this is the order, this is the increasing order in which the gases will come out. How can we obtain pure copper sulfate from an impure sample? We take approximately 5 gram impure sample of copper sulfate in a china dish. We dissolve it in a minimum amount of water. We filter the impurities out. Then we evaporate water from the copper sulfate solution so as to get a saturated solution. Then we cover the solution with a filter paper and leave it undisturbed at room temperature to cool slowly for a day. We observe that because we have let the water be evaporated, all right, so obviously when we are letting the water evaporate, we are letting the amount of solvent in the solution to decrease, right? So when we are coming to that stage, so a point will come when the water won't be able to hold all the amount of copper sulfate, right? So what will happen is the amount of copper sulfate will start separating from the water solvent, and that will happen by the process of crystallization. Crystals of copper sulfate in the china dish are obtained, and these crystals, they are more definite in shape than the previous crystals. So we obtain pure copper sulfate from impure sample using this crystallization method, where we cause the solvent to evaporate and we get the pure crystals of the solute. What is crystallization? Crystallization is a process that separates a pure solid in the form of its crystals from a solution. So the solute should be a solid, solute should be a solid, and the solvent should be a liquid, and then only we can have this process of crystallization. For example, the salt that we get from seawater can have a lot of impurities in it, and to remove these impurities, the process of crystallization is used. How crystallization is better than evaporation? Because some solids, they decompose, like sugar may get charred on heating to dryness. Alright, so if you try to heat it, then sugar may decompose, it may char, right? So, and there may be some impurities that may remain dissolved in a solution even after filtration. But when we evaporate the solvent, we are allowing the solute to remain in a very pure form, right? So evaporation, these contaminate the solid, okay? But through the process of crystallization, this is happening because it is allowed to evaporate and we are getting the pure solute. We are getting the pure solute. Application of crystallization: purification of salt that we get from seawater, separation of crystals from alum or fitkari from impure samples. So alum is used as an aftershave stone, and obtaining sugar from sugarcane. Question 1. How will you separate a mixture containing kerosene and petrol? Difference in their boiling points is more than 25 degrees Celsius, which are miscible with each other. So we are having two miscible liquids, alright, and the difference in their boiling point is more than 25 degrees Celsius. So we will use the process of distillation to separate the components of this mixture. Name the technique to separate butter from curd. Centrifugation, right? We saw this in that cream from milk example. Then salt from seawater, we just saw this. Crystallization, right? We just saw this crystallization. And camphor from salt, sublimation. Question 3. What type of mixtures are separated by the technique of crystallization? So by the technique of crystallization, we can separate those particles that have the solute as the solid, all right, and the solvent as the liquid. Solvent is the liquid, so that the solvent can evaporate and we can get the pure crystals. So these types of mixtures are separated by these heterogeneous mixtures are separated by the technique of crystallization. And even homogeneous mixtures such as seawater.